Bismillahirrahmanirrahim, dear students. In the last lecture, I told you about we start chapter number 7, chemical equilibrium. So just I gave some introduction about the reversible chemical reactions and irreversible chemical reactions. So just we done this one. Now this lecture number 48, chapter number 7, chemical equilibrium, and class 11. So here are the example for the reversible chemical reactions. So we have to explain this one. And you have water in the gaseous state, carbon monoxide in the gaseous state, and to form hydrogen gas in the gaseous state, carbon dioxide gas in the state. So when all the reactants and products are in the gaseous state, we call them homogeneous equilibria. They are the one topic. Homogeneous equilibria, all are in the same phase, same state. So when we say that chemical equilibrium, in the last lecture I told you that when the reactants react, these are the reactants. Initial concentration of reactants is very high. Initial concentration of the reactants is very high. If you see the graph here, I am going to draw the graph. This is the y-axis, and here this is the x-axis. This is the time in seconds, and this is the concentration. Okay. So initial concentration of reactants maximum. Initial concentration of the reactant is maximum here. So this is the maximum concentration. Concentration of the water, same number of moles, and concentration of the carbon monoxide. So initial concentration of the reactant is maximum here, and the concentration of product is zero here. So concentration of hydrogen and concentration of carbon dioxide is a zero because the chemical reaction is still not started. So initially the concentration of reactant is a maximum and concentration of the product is minimum. So as the water in the gaseous state and carbon monoxide are gradually used up in chemical reaction start. Chemical reaction start, used up. The chemical reaction will go forward reaction. Gradually it shows forward reaction. As the molecule of hydrogen and carbon dioxide gas are accumulate, when they are accumulate, concentration of the product is going to be increased, accumulate. Then after accumulation, the reverse reaction happens. The reverse reaction starts with the increase in concentration of hydrogen and carbon dioxide gas. More and more, the collisions per second between these molecules occur. Therefore, the reverse reaction proceeds with the increasing speed because you have a more number of moles of the product. Means accumulation of the product is more, then the frequency of collisions will be more and the chemical reaction goes to reverse direction. Therefore, reverse reaction proceeds with increasing speed. This means that forward reaction starts with a maximum speed when there is an accumulation of the product. When they accumulate, then the chemical reaction starts to go backward. Then the speed of the reverse reaction is going to be increased. This means that forward reaction starts with the maximum speed and gradually slow down. Whereas the reverse reaction starts zero, reaction starts zero from here, speed and gradually increases its speed. So students, this is the forward step, hydrogen, so water, carbon monoxide gas to form hydrogen gas, and plus carbon dioxide. This is the rate of forward. This is a forward step. This is the rate of forward step. This chemical reaction is going to be forward reaction. Then accumulation taking place for the hydrogen and carbon dioxide gas. Then reverse reaction happened. Hydrogen gas, carbon dioxide gas changes into water in the gaseous state and carbon monoxide in the gaseous state. This is the reverse happening. So students, what happened? You are seeing that concentration of forward is going to be, now initially the graph is steep. The steepness of the graph is that the concentration of the reactant is going to be suddenly decreases, and the concentration of the product is suddenly increases like this. So this is going to be decreased and this is going to be increased. So the point they reach where they cross here and then become horizontal like this. Constant now. Then the concentration become constant. Initially, the graph had a more steep because concentration rapidly decreasing of the reactants and change into product, and concentration of product is going to be increased rapidly here. Increasing with a great more rate and decreasing with a more rate here. So it means that slowly and gradually the rate of both become equal. Eventually the time will come, then both rate of forward and rate of reverse will proceed with the same rate. Means the rate of forward step and the rate of the reverse step will proceed with the same rate. It means that no significant change in concentration of the reactant side and product side. These are the reactant side, these are product side. You are seeing horizontal. So this state is called equilibrium state. Eventually, the time comes when both reactions proceed at the same speed. The reaction at this state is said to be in the chemical equilibrium. The concentration of reaction and products become constant. The concentration of the reactant forward and the product reverse is going to be constant. See, this is a constant, no change, no significant change, horizontal, both. So this state is called equilibrium state. Now, if you are not going to be impose some external conditions, you are not going to be change temperature, you are not going to be change concentration, you are not going to be change pressure. If we impose some external conditions, then the chemical equilibrium will be disturbed. You done in grade 10 according to Lichert-Clear's principle. When you impose some external changes, then the chemical equilibrium will be disturbed. Otherwise, if you are not going to impose any change, then the chemical equilibrium will be always in the equilibrium. So the state of reversible reaction at which compositions of the reaction mixtures does not change. Both composition of the forward state and reverse state is the same, no change. Then this is called a chemical equilibrium, and the state is called chemical equilibrium state. So we have plot the graph, you can see this one. So since the concentration of reactants products become constant, already I told you, it may appear that the reaction has stopped. This is a question. When the equilibrium is established here, no significant change in the concentration of the forward state and reverse state formation of products and reactants, so we assume that chemical reaction stop. But listen me carefully here. In the equilibrium system, chemical equilibrium never stop. Chemical equilibrium never stop. It's not true. On the microscopic level, there is an excited activity. Individual molecules are continue reacting. The difference is only the rate of both steps, forward or reverse, are same, 100% same. So then we call it is a dynamic equilibrium. We call it dynamic equilibrium. Individual molecules of products also continue to combine, but the rate of one process is exactly balanced with the rate of other. Both rates are 100% balanced. Therefore, this is called dynamic equilibrium. The system is dynamic because individual molecules react continuously, no stop. But the rate of forward and reverse is equal. It is at the equilibrium because no net change takes place unless you are imposing the change on the system. Otherwise, this will be same. So this is called a chemical equilibrium state, dynamic equilibrium, forward state, reverse state. Both states are 100% equal. Rate of forward and rate of reverse. You will get the equilibrium. Initially concentration drops, decreases very rapidly because products are formed very rapidly. At the end, the chemical reaction will become slow and the rate of forward and rate of reverse become equal. The equilibrium is established. So this is the introduction of equilibrium. Now students, there is the equilibrium constant. Equilibrium constant is denoted by K C. This is called equilibrium constant. While we are going to explain the equilibrium constant law, we have to explain law. This law is called law of mass action. Law of mass action, two scientists, C.M. Goldberg and P. Webb. In 1864, they put forward the law is called a law of mass action. You learn in the grade 10. This law states that the rate at which the substance reacts, means the rate at which the reactant reacts. The rate at which the reactant substances react is proportional to its active masses. Active masses means the masses which are present in the balanced stoichiometric equations, number of moles of chemical reaction is proportional to the product of active masses of the reacting substances is called law of mass actions. You must write this law. There is another definition also. The rate of chemical reaction is proportional to the product of molar concentration of each reacting substances raised to power equal to its stoichiometric coefficients. Number of moles. When you write the balanced chemical equation, we call stoichiometric equation. You done in the chapter number 1. So these stoichiometric equations, they have some coefficients to balance in. So when we write in the law, you must put in the raised power. So we have active masses, I told you, concentration of the reactants and products in moles per decimeter cube. Concentration, unit of concentration is moles per decimeter cube, and concentration is denoted by the square brackets. So I am going to write with the general equation. This is the A reactant. These are the number of moles, active masses, moles concentration, plus B reactant in the gaseous state. These are the number of moles in the balanced chemical equation. It is in the equilibrium state, and this is the C, and the C number of moles in the gaseous state, and this is the D product and number of moles of D in the gaseous state. So this is the equilibrium. According to the law of mass action, according to law of mass action, the rate of chemical reaction is proportional to product of the molar concentration of each reacting substances raised to power equal to stoichiometric coefficients in the balanced chemical equation. So dear students, if we see A, B, C, D, A, B are the reactant and C and D are the product, small a, B, C, D are the coefficient in the balanced chemical equation, and their concentration is moles per decimeter cube. Now first, rate of forward reaction. Rate of forward reaction means like this one. According to law of mass action, rate of forward reaction is directly proportional to concentration of the reactants in the raised power balanced chemical equation. So, dear students, this is the square bracket which shows concentration of A reactant with the coefficient of the A, concentration of the B reactant with the coefficient of the B. This is the rate of forward is directly proportional to concentration of the reactants with the raised power in the coefficients in the balanced chemical equation. So this, if we are going to remove this proportionality sign, then rate of forward reaction must be equal to, you have to put a constant which is called Kf. K is called a rate constant, where K is called rate constant or proportionality constant. Rate constant or proportionality constant for the forward step. Rate constant for the forward step. Rate of reaction of the forward step. This is the constant. So concentration of A, power A, and the concentration of B, the power B. Same case, number 2, rate of reverse reaction. Rate of reverse reaction. So this is the rate R for reverse, directly proportional the concentration of the products, the number of moles in the coefficient balanced chemical equation, the C, power C, and concentration of D, power D. So it must be equal, rate of reverse must be equal to KR. I already told you that K is a rate constant. Now this is a rate constant for the reverse reaction, or rate constant for the reverse step. So it is concentration of the power C and the concentration of the power D. Like this one. So dear students, when the chemical equilibrium is established, both rates are equal. The rate of forward must be equal to rate of reverse. Rate of forward must be equal to rate of reverse. So that is why how I can write this equation. So Kf, rate constant for the forward step, concentration of A power A and concentration of B power B must be equal to the K R for the reverse step, concentration of C power C and concentration of D power D, like this term. And we are talking about the equilibrium constant Kc. So equilibrium constant Kc is equal to rate constant for the forward divided by rate constant for the reverse. Rate constant for the forward is equal divided by rate constant for the reverse. So dear students, there is one very important thing is that this Kc equilibrium constant, when you write this or this equation in one state, this is the whole derivation of the law of mass action. But if you write in the one state, so you should mind that on the numerator side must write the concentration of the products must appear on the numerator side divided by concentration of the reactants. The reactants must appear denominator side. This is the Kc is equal to Kf over Kr. So this is the Kc. These products appear to the numerator side. Reactants appear always to the denominator sides. So students, Kc is called an equilibrium constant, and the square brackets indicate concentration of chemical species in the chemical equilibrium. Thus the equilibrium constant expression for any chemical reaction be written from the stoichiometric balanced chemical equation. Kc equilibrium constant can be written from the balanced chemical equation, and the step I told you, which is a very important, don't mistake it. Concentration of products are taken in the numerator and the concentration of reaction is in the denominator side. So this is the law of mass action, very important topic. The whole this chapter is based upon this law. Law of mass action we have to apply in all the topics. So please, you have to derive, you done in the grade 10 also. Now conditions for equilibrium. Conditions for equilibrium. So general equation again I am writing. Rate of forward, rate of reverse, like this one. So important features of the equilibrium constant expression as follows. Kc equilibrium constant. C indicates that concentration of the reactants and products in moles per decimeter cube at equilibrium state. Dear students, the value of the equilibrium constant is independent of the concentration, but it depends upon temperature. It depends upon given temperature, has its own value at particular temperature. So we start reaction with the pure reactants or pure products or any composition in between. The value of Kc remain unchanged unless you change the temperature. Now equilibrium constant is related to the coefficients of the balanced chemical equations. The concentration of the product are placed on the numerator side and concentration of the reactants placed on the product side. This point number 4 is very important and you have to concentrate it well this point. The magnitude of the Kc, when Kc is high or Kc low, magnitude. The value of equilibrium constant. The magnitude of Kc indicates the position of the equilibrium. The magnitude of the equilibrium constant shows a position of the equilibrium. So the point is that when Kc is less than 1, when the value of equilibrium constant is less than 1, then denominator, this is denominator. When you write the equation in the Kc form, reactants appear denominator side and products appear numerator side. So if the value of Kc is less than 1, then denominator means reactants is greater magnitude in the numerator. Means reactants magnitude greater than that of the products. Concentration of the denominators greater in magnitude than the numerators when the value of Kc is less than 1. This is one condition. Second, when the value of equilibrium constant is greater than 1. When the value of equilibrium constant is greater than 1, then reverse happen. Then numerator is greater in magnitude. Numerator means concentration of products. Greater in magnitude than that of the reactants. So these are the very important conditions 1, 2, 3 and 4 you have to remember. Dear students, in grade 10, you done the units. Suppose hydrogen iodide decomposed to form hydrogen gas and iodine gas. Okay? So the Kc equilibrium constant is equal to concentration of products numerator side, concentration of reactants denominator side. This is the value of Kc. So dear students, when the number of moles on the both sides are equal, then it has a no unit of Kc. Moles per decimeter cube, moles per decimeter cube, moles per decimeter cube square. They are all cancelled out. That's why there are no unit here. But in the case of when you are putting nitrogen gas plus hydrogen gas to form 2 moles of ammonia gas like this one. So on the both sides, number of moles are different. Number of moles are different. So equilibrium constant, concentration of product raised power 2, concentration of the reactants, hydrogen is a power 3. So if I write the Kc units, then this is the moles per decimeter cube for one ammonia, moles per decimeter cube for other, divided by moles per decimeter cube for the nitrogen, and 3 moles per decimeter cube 1, moles per decimeter cube 2, and moles per decimeter cube 3. There are 3 ones. Now it is easy for you. This is going to be cancelled here, this is going to be cancelled here. Now 2 cancelled, you have a 2 here. So they are denominator side, 1 over this one. So this is the mole and mole, this will be a per mole square. This is a mole and this is a mole, and if we are going to make it numerator, this per mole square. This is a per decimeter cube, this will be a decimeter 6. This is a unit. You done in grade 10. Per mole square decimeter 6 is a unit of the Kc in this chemical reaction. Dear students, here are some other also you are going to write the value of Kc. Unit of Kc are given here. If you have one, I am going to solve, then you have to solve you at home. So, sulfur dioxide gas, oxygen gas, to give 2 moles of sulfur trioxide gas. So this is the stoichiometric equation. Kc is equal concentration of sulfur trioxide, concentration of sulfur dioxide, and concentration of oxygen. Dear students, concentration of sulfur trioxide, moles per decimeter square, moles per decimeter, they are cancelled. Both are cancelled. So you have only the moles per decimeter cube for the oxygen. Because this is a square, this is square, both cancelled. So it means these are the per moles decimeter cube, like this one. So dear students, we have to calculate other also units. Practice for this. So we continue this chapter inshallah. Thank you very much.